Hello, everybody. We are going to have now the second but last meeting on the ALF Basics. And there's a small change in the program. It doesn't change the times, just the content of a part of it. So now we're going to have explained the talk by Florian on the hopping part of the code. Then we're going to have the contributory talks. We are going to talk just after a break, and then a second break, followed by explaining the Theorem Monte Carlo talk by the last Theorem Monte Carlo talk by Professor Assad, and together with his own ALF Basics talk, which is going to be on the models in the package, included in the package. And that's going to be made a bit shorter so that Johannes can then talk about the package as a whole. So we noticed that it's missing an overview of how we have been presenting the different parts, but it's missing an overview of how everything is together, it's linked together, how everything works together. So it's overdue that we do that, and we're going to do that then later this afternoon. But now, please, let's watch the talk by Florian on the hopping part of the package. Florian.
Thank you, Jefferson, for the introduction. And it is now my pleasure to introduce you to some of the aspects of specifying hopping matrices within the ALF package. So what are we going to cover in this session? First, we will talk a little bit about the hopping Hamiltonian. Then I will introduce to you some notions of the checkerboard decomposition. You have already heard that term in some of the talks. We will talk about what we believe are the most general entries of the hopping matrix, how you can, in the sense, general in the sense what makes physical sense. Then I will walk you through an example on the Hubbard model again, and how to use the operator type for specifying the hopping matrix. And then I will quickly present you some of the predefined hopping structures that are already available in the code. So again, we have to look again at the full Hamiltonian, consisting of basically three parts: the hopping Hamiltonian, the interaction, and the interaction with fermions with an Ising-like variable. And for this talk, we are restricting ourselves to the hopping Hamiltonian, given here. And we have to ask ourselves which constituent parts does it have? It does not have as many moving parts as the interaction vertex that we introduced yesterday, but nevertheless there are still some variables available. First and foremost, you have interaction matrices that specify this quadratic form in the fermionic operators T, X, Y. So these are the spatial indices, X, Y, and you can have MT numbers of them, and you can have NFL, so flavors of the hopping matrices, and every flavor and every number of them can have a different hopping matrix for specifying this quadratic form. Additionally, you have to specify the dimensionality, so most of the time this is the spatial volume, and the number of colors. As already outlined, the number of different hoppings is either given by the model that you're trying to consider or trying to simulate, or it could be that you want to use checkerboard decomposition for optimization purposes. This will also lead to an increased number of different hoppings.
Florian, you have that black box covering your title, the title of this slide.
Yeah, these are zoom controls which I cannot move.
I see. No, this box is fine, but there's a smaller one. Yeah, exactly.
Yeah, these are, I don't know. Can I move them to the bottom? Maybe that button.
Yeah, that might, at the moment it's better like that. I don't know if for further slides. Okay,
yeah,
okay.
so let's see. Here is nothing important, so let's keep it there. Where was I? Okay. So For the checkerboard decomposition, it's important to know that most of the time, basically all of the time, we require only a single operation. We need to be able to exponentiate the hopping Hamiltonian and perform operations with the exponentiated hopping Hamiltonian. Because if we use that, then we can again apply the Lie-Trotter formula to split up a sum of matrices into a product of exponentiated matrices subject to an additional error. And now the task that we have to consider is to find a decomposition of a given hopping matrices of a given hopping matrix as a sum of new matrices, such that for each hopping matrix we have in some sense we can evaluate the exponential more efficiently. The prototypical example here is the one-dimensional chain. It has a hopping matrix of this form. So this is a 9 by 9 matrix. 9 by it's a chain with a length of 9 ions with open boundary conditions, and it with next nearest neighbor hopping. So you can only hop from between, for example, from 1 to 2 and from 2 to 3 and so on. And this can be decomposed in two families, so-called families of hopping matrices in this particular form. I should explain maybe. White means that the matrix is 0 in that part, and orange means that the matrix has a 1 or the amplitude of the hopping at that entry. So if you do this decomposition in that form, you will notice that each matrix decomposes into small 2 by 2 blocks. So for example, this one over here, this is a separate 2 by 2 block. This is a separate 2 by 2 block. And the matrix the entire matrix is block diagonal in these 2 by 2 blocks. So it just boils down to exponentiation of small matrices. And if we do that, we can use the property that a subblock of this particular form with entries Cj that are located here can be exponentiated in that form by introducing hyperbolic functions of these entries. So this was the 1D example. How does this generalize to higher dimensions? I have taken the lattices you've already been presented by Jonas, and you also find them somewhere in the documentation. If you look at these lattices now, you find that you have to, at each ion, you have to introduce separate bonds of a separate index. Here, the families have been denoted by colors. So all red bonds will be in one family, all green bonds will be in one family, all blue bonds will be in one family, and all black bonds will be in one family. Similar construction also holds for the Honeycomb lattice down here. So essentially, finding this type of decomposition boils down to a graph coloring problem. How can I decompose this matrix so that at every vertex the outgoing edges have different colors. So at every vertex, there may not be two colors of the same type, which is in the particular examples here, it's always fulfilled. And now you can ask the question: how many families do you actually need? And the answer is given by Weissing's theorem. So given a simple graph G with a maximum vertex degree delta of G, the vertex degree is similar to the coordination number. It counts how many edges does a particular vertex have, and the maximum vertex degree is if you consider that onto the whole lattice. It need not be regular. And then the number of families is given by the so-called chromatic index chi prime of G, and it is known that this can only take two values. Either it is the vertex degree or it is the vertex degree plus 1. So all graphs in this world decompose into these two families. To decide to decide in which class your particular graph is an NP-hard problem, but it is known that for bipartite graphs, the chromatic index is always equal to the maximum vertex degree. Either you figure that out yourself, or you use libraries for doing this graph decomposition. Here's I've written down a particular implementation here, which implements the algorithms given in this paper by Cheryong Lee from 2013. And if you're curious about generalizing this to higher orders, this is the archive reference down here. So this was it for the checkerboard decomposition, what actually this notion actually does, how to decompose a general matrix into a set of easily exponentiable matrices. So this would be the checkerboard decomposition. Now we have to consider the fact what can be the most general entries of the matrix that we want to consider. What can these entries be? And we've thought long and hard about it. And this is what we could come up with. So this is a general quadratic form in the fermionic operators C dagger and C, specifying the entries of the matrix T. So there are a lot of indices and moving parts in here. So K and J denote the lattice indices. These are the indices of the lattice that you can consider. Delta and delta prime are now orbital index for having the flexibility that in the lattice you also have separate orbitals. With A specifies vector potentials for if you want to include magnetic fields into your particular model. This is, what was it? The so-called Payal's phase substitution for introducing magnetic fields. TS is the, let's call it non-magnetic hopping matrix. So that would just be is most of the time just determined by your lattice structure, which are the connected bonds in your lattice. And on top of that, you could also include twisted boundary conditions. So that's why we have to specify the boundary conditions when we move from one boundary to the other. And there you can introduce a twist by these scalar gauge function chi, and which has to be related to the vector potential by this relation, the so-called Landau gauge. To guide you to the relevant entry of the documentation for this and the relevant code, we have written a function that gives you these entries where you just have to specify the vector potentials and the number of flux quanta. And one thing to note, you can have different numbers of fluxes in different directions of the lattices. This flexibility is also there. And the function you want to look for is called generic hopping. Which gives you the entries of a hopping matrix, which with this full flexibility. But now let's come to something simpler. So just that you see how a simple example would work. So this is the Hubbard model on a square two-dimensional lattice. I assume it's given by this innocent-looking Hamiltonian which specify a quadratic form in the fermionic operator C dagger and C. The hopping matrix Tij is spin independent and only connects the nearest neighbors here on the lattice. So the graphical representation of this matrix in a graph-like language would be this. So you have a vertex sitting here, which is connected to its next nearest neighbors via 4 bonds. And the matrix representation of this graph, the adjacency matrix basically is given by this. So you have the next nearest neighbor hoppings along this direction, for example, assuming you have a Z-like enumeration of your ions, are these entries. And if we're here in A1 direction and the next nearest neighbors in A2 direction, are given by these super diagonal and sub diagonal over here. And now it basically boils down to encoding this matrix into the code at the right place. So again, let's look how similar to yesterday. Let's look at the respective place in the Hamiltonian. So we have written our module for the Hamiltonian, and you have what you need to do. You need to fill this array of operators, op t. T denotes the hopping matrix, and it's given down here. So this has to be available. If this is not the case, ALF will not work. On top of that, you also need the other parameters, the dimension, the lattice volume, the number of flavors, colors, and the respective parameters of your Hamiltonian. So for the Hubbard model, we have the hopping amplitude, the coupling strength of the interaction, and maybe a chemical potential. Just a note: chemical potentials usually are on-site interactions, which would fill up the space at the diagonal. Okay. So how does the operator look like? There are a couple of user visible parts. The operator is similar to yesterday, a structure that you have to, the structure that you have to fill for specifying it. It has an effective dimension, op n, and it has this op o array where you specify your hopping matrix. The O matrix is related to the full hopping matrix via introducing the projectors. Most of the time for the hopping matrix, you don't need the projectors, but the freedom is there to use them. If your hopping matrix has a certain sparsity pattern that you want to be able to exploit, then you can do it via the projectors. We have op g, which is the coupling strength. Usually it's given by delta tau times some hopping amplitude. So this is not the matrix from before, it's the scalar the global scalar prefactor of the matrix. And you might also have to specify the offset that is given in the operator, but which is not used. I can't think of a case where this is used for the hopping matrix. So with this full information, we can recover the hopping matrix here, and we can efficiently evaluate the hopping matrix since these nice representation holds between the projectors and the full matrix. We do have certain conventions for specifying a hopping. So usually you move that to a separate subroutine. In our case, it's called something like ham hop for setting up the hopping matrix. Here I've taken up the example of the two-dimensional lattice. First, you have to allocate the array, so that Fortran knows that you want to allocate space there. So it has the number of flavors, and it's only a single for the Hubbard model. It's only a single for the Hubbard model without checkerboard decomposition. It's only a single matrix. That's why it's 1 time n flavor, the size of the array. Then for every flavor, you have to set up the internal storage of the operator via op make. And then you have to fill up the operator with its entries. That is done via the next loop. So you loop over the entire lattice. Here is a call to the lattice module presented by Jonas in an earlier talk. Here you get the nearest neighbors in x direction, the index, and you set the entries of these neighbors in the matrix to the hopping amplitude. In our case, it's minus half t. And then if you here it's protected by an if statement, so the code can switch dynamically from can go from 1 dimension to 2 dimensions, or if you are in or you can also consider ladder models with that. Then you do the same for the y direction. You ask for the neighbors in y direction and also set them to the hopping amplitude. If present, you set the diagonal term to the chemical potential. So this is done here. And since this is a full matrix, the projector is basically unused, but nevertheless, you have to specify the data in a correct way. So this is done here. The delta tau, the global delta tau prefactor is here absorbed in op G. And alpha is set to 0.0 since there's just no scalar shift present. After you specify all your entries of the matrix, you have to call op set onto that operator to give it to set up the internal auxiliary storages that we need for proper operation. If you have done that, then you can call ham hop in your initial subroutine ham set, which forms the entry point of ALF for specifying your Hamiltonian. So this would have been the case if you specify the hopping matrix manually, just by specifying hop t. That's the information that ALF needs for working. But of course, we are providing you with predefined structures, so that you don't have to do this step for every type of lattice again. Using the predefined structures is a three-step process basically. First, you have to call something like set default hopping. With a star, I have denoted here that we have various predefined default hoppings available. You have to choose the right one for your issue, for your problem. From this function, you get a so-called hopping matrix type back, which encodes all the information that is required. And then you have to convert the hopping matrix type to the op t matrices, and this can be done by a call to predefined hoppings set op t. This sets the op t array that you have seen in the Hamiltonian. And now we move on to presenting you some of the default hoppings that are already available. We do already have the hopping on a square lattice in a very general form. So this is given by this Hamiltonian with a magnetic field, with a hopping matrix T, with orbital degrees of freedom, with a chemical potential, and this full multitude of parameters can be obtained via a call to set default hopping parameters square on the square lattice via a call to this function. But bear in mind that you have to give it all this information. So T vector, a vector of T matrices, a vector of chemical potentials. I think it's not a vector of T matrices, it's a vector of scalar prefactors of the T matrices, a vector of chemical potentials, a vector of the twists in X direction, in Y directions, the flavors. The lattice needs to be known to this function. So you have to specify all this in advance, and then you can call this function, and it will set up then you get information about the respective hopping matrices. Another possibility that a lot of people are probably interested in is hopping on a honeycomb lattice. This is given by a similar expression. And you can look out for the function called to set default hopping parameters honeycomb, and it will give you a hopping matrix type with the required information for getting the hopping matrix of a honeycomb lattice. I will just point you towards the documentation for other possibilities, since they have Hamiltonians which are longer than what I could squeeze onto the slides. We also have predefined hoppings available for bilayer systems, for the square lattice case, and also for the honeycomb lattice case. So you can do bilayer honeycomb simulations. And another possibility would be to study n-lag ladder systems. So there's also predefined hopping available for that. Okay, now let me come to my last slide. What we did not cover here in this talk now is the coupling to Ising fields. It's currently there's not many. Currently we don't have that many simulations using it, as far as I know. If you want to find more out about that, then in the most current up-to-date version of the documentation, there's a chapter on C2 gauge theories, which pointed towards the literature and details and gives you maybe some more of the context. And also another thing, if you are interested in writing your own predefined hopping, if you want to contribute that at some point to the ALF project, then you would have to figure out the internal structures of the hopping matrix type so that our routines can work with that. And yeah, that brings me to the end. And so thank you for your attention.
Thank you, Florian. So if anyone has questions, now is a good moment. We do have some time still before the break, and the questions actually can extend over the break. That's not a problem.
Yeah, I had a first question. It was about the predefined square lattice that you presented in the previous slide. Yes, here you show that we see that T has a dependence on S only. Is it possible to include direction-dependent hoppings, that is along X or Y axis, for example? Or do we have to do it ourselves? Because it was from the exercise 1B from the tutorials, they said we could from the plain vanilla do the same thing in the Hubbard model directly, but it seemed that in the default hopping parameter square, this was not really simply possible.
That's not, can I comment on this?
Yeah, of course.
There's an exercise 1B, which yes. I did this morning with Eduardo. And you have to work a bit, that's true, but it's just changing one or two lines in the hopping for the predefined square lattice, and then you can put a TX, TY. But admittedly, it's a bit tricky. You have to understand, as Florian was saying, you will have to understand the structure. So that is, of course, more involved.
Okay, thank you very much.
There's something more in the chat, as far as I see.
If ALF includes a predefined structure for a 3D lattice, like a cubic lattice. And the second question, what about nearest neighbor hopping amplitudes?
We don't have predefined structures for 3D lattices, in the sense that you could emulate maybe these things by abusing the orbital degrees of freedom and doing the right things. I don't know that. Nearest neighbor hopping amplitudes. So you want, for example, yes, it's a similar question as before. The TX should be different.
Sorry, I meant next to nearest neighbors. So to have nearest neighbors in amplitude T, and then like the next to nearest neighbors T prime, for example.
I don't think so that we have predefined structures for that. So you would have to set them up yourself, or either write the right new predefined structure for that, similar to what
you mentioned. Thank you.
Okay, and then another question by Nicholas is for the predefined square lattice. T vec depends on S.
Yeah, that was already answered. Thank you.
All right. Okay. You just came true.
No problem.
I just saw it now. And
I have a question, Jefferson, or Florian.
Yeah, better.
If I give you a hopping matrix, which consists of essentially of a graph with different connections between the points of the graphs, can you automatically write a code that will generate a checkerboard decomposition? Because we do this manually for each lattice for the moment, so it's very, very cumbersome. It's a lot of work. The question is,
I can't answer this in the present tense, but in the past tense, you have this library available, right?
So did we so did you try it? Could we try this?
Of course, if people have time, I can basically show you that how I do that and plot things. So, and with a couple of examples.
So you would generate the families, all the structure we could have. You would just fill in the matrix, and then all the checkerboard lists and everything would be automatically produced.
So you get a yes, with one caveat in the sense. So let's go back.
Right.
To down here.
Right. Exactly.
As I said, finding out for a general graph, finding out whether your particular graph has either. So the question is, are you optimal in the sense?
Right.
The optimal number of families, and deciding that is an NP hard problem.
I understand this.
So maybe you can write a code, but it won't be efficient. But in the classical sense, it might still be efficient for the lattices we consider. I don't know that. Okay. What I have written is a code that does not try to find the optimal number of families, but tries to get by with delta G plus 1 number of families. Most of the time, for all regular lattice that I put it up to, it found also the optimal number of families.
Okay.
So if you do a one-dimensional chain, you get 2 families. If you do a one-dimensional chain with next nearest neighbor hopping, you get 4 map families. If you do a 2-dimensional lattice, you also get 4 families. But in the worst case, you can't decide. So it does not decide whether you have the optimal number of families.
Okay.
It gives you the number of families within these bounds.
But in principle, that would be an add-on we could put in, at least to propose. So that would be much easier, because now if you want to program the new lattice, then you have to provide also the checkerboard manually.
Exactly. So so that for a given matrix, it decomposes the matrix into the number of families. In the worst case, for a very, very fancy lattice, you are off by 1 family.
Right.
But it's automatic, yeah. And I have tested it. So the code that is available on my laptop from 2 years ago, I could decompose in, I don't know, in a couple of seconds, matrices with 1 million entries and thousands of families.
Okay, that won't happen in the ALF, but okay.
You don't know.
Thank you.
Nathaniel raised his hand. You can make a question.
Hi, I have a question about the decomposition, the checkerboard decomposition. Is it unique in the sense that there is just one checkerboard decomposition for one type of lattice?
No, it's definitely not unique, since you can rearrange. You can permute the entries of the matrix. So this would still give the same graph, and yeah, I've seen multiple, or stated differently, you can get different checkerboard decompositions out of the code, depending on basically where you start to look in the matrix for connections.
Yeah, it's even the case that there are better and worse checkerboard decompositions. So different checkerboard decompositions could have different systematic Trotter errors. So that's also a thing to consider.
Okay, thank you.
I still have another question, Florian.
Great.
Would it be possible to, I mean, we could use fast Fourier transforms instead of doing checkerboard decompositions. Would that, would that be not an easier way to go as a default? I mean, what would be the loss? I mean, it would be not much slower, right, than doing a checkerboard decomposition.
You mean for, well, the
fast Fourier transformation would be n squared log. I mean, if n you have endpoints, would be n squared log n, something like that, correct?
Yeah, yeah.
And the checkerboard decomposition is n squared.
Yeah.
So, yeah. So maybe for the default, I mean, if we don't, so I'm always thinking about if somebody wants to program his own lattice and he has to provide this stupid checkerboard decomposition. I'll take away stupid, but it has to provide the checkerboard decomposition, and that's a lot of work. So we could put a default, which would be just using fast Fourier transform to do the hopping matrix multiplication.
Certainly you can do that, but how is it? You probably right for the fast Fourier transform to be efficient, it needs to be what is it? A circulant matrix type. So the notion of translation symmetry.
Okay, so we do have this. We do have the translation symmetry.
Then you should be then you can do that, yeah. But is it more efficient? Well, where you have then it's technically it's not, since it's n squared versus n squared log n. But the fast Fourier transform is fast.
Right. So that's maybe one thing to put on the list, right? A thing to try. Thank you.
So if you don't have further questions, we can start our break, and then we're gonna be back at 2 our time, Berlin time, for the first contributor talks. Let me, Florian, is it okay if I share my screen instead of yours?
Sure, go ahead.
Let me quickly show you. So we're gonna have the first talk of today at 2 is gonna be by Miklos Werner from the Budapest University of Technology and Economics. And the second talk by Joël Hutchinson, now at the École Polytechnique. Okay, so see you at 2.